Now let's consider a slip in this single crystal. You are applying a tensile force F. This is the slip plane. So this tensile force will act as a shear force on this slip plane. That shear force will be F cos lambda. This is the angle lambda. So this is the resolved component of this force. So the shear stress which is acting on this slip plane will be shear force Fr divided by A, area of this slip plane, area of this slip plane. So you can calculate the resolved shear stress will be tau r equal to sigma cos lambda cos theta. So ultimately the tensile stress which you are applying, it is acting as a shear stress in that slip plane, which is equivalent to sigma cos lambda cos phi. So this resolved shear stress reaches a critical value where plastic deformation initiates, called as critical resolved shear stress. So ultimately we will have to calculate the value of this critical resolved shear stress, that is minimum stress required to initiate slip. So to calculate this shear stress, let's consider this atomic model. These two are the slip planes. You are applying a shear force to these planes and it moves from position 1 to position 4, and this complete motion of one interatomic spacing has been considered as a sinusoidal wave motion of this. So as you apply shear force, you have to reach a maximum value where the slip will takes place. Then it comes to the position number 3, and then again in the reverse direction. This is the sinusoidal wave motion, and the equation of this sine wave equation is tau equal to k sine 2 pi x by b. Here, this is the interplanar spacing d. This is the Berger's vector, because Berger's vector is generally half of the close packed direction in general, as you have studied in the crystal imperfection. So by this simple mathematical calculations, we have reached a value that tau CRSS equal to mu by 6. Mu is nothing but the shear modulus. So you can say that if you know the shear modulus, you divide it by 6, you will get the critical resolved shear stress. So shear modulus you can calculate experimentally. So my question is that if some material shear modulus is 200 GPa and you divide it by 6, so tau CRSS will be nearly 30. Do real crystal follows the above theoretical prediction? In this we have considered an ideal crystal. So because in general experimentally we know the shear modulus of all the materials, and you divide it by 6, you will get the tau CRSS. We have some tau CRSS calculation here. So generally this mu by tau equal to 6, right? But when we calculate the CRSS of real crystal, this value is very, very high. This value is very, very high. It means the shear stress required to initiate slip is far, far less than the theoretically predicted model. So this is the CRSS. We say I give, if it is a 120 GPa is shear modulus, you divide it by 6, you will get 20 GPa, but here the value is only in megapascal, 0.5 megapascal, 5 megapascal. This value is far, far less. So the reason for that is the value, why this value is so low, is because of the presence of dislocations. Means the slip is taking place by the moment of dislocation. The moment of dislocation, that is climb And this glide motion you have already studied in the crystal imperfection chapter. But again I'll explain here. What happens? This is a ideal crystal. Let us suppose this ideal crystal is having one dislocation which I have shown here. If you apply shear force to a ideal crystal, then there will be a complete slipping of the plane. This is the dislocation here. When you apply a shear force, this is the slip plane. When you apply a shear force to material which are having dislocation, what happens? Because this is a distorted region, you have studied that. Here is a compressive stresses, here is a tensile stresses. So this dislocation started moving at much lower stress than the theoretical, because this is already distorted. The energy of this around this dislocation is very, very high. So you are applying a shear force. Before the complete plane slips, the dislocation start moving and the plastic deformation initiates. So our purpose was now to calculate what is the stress required to move a dislocation. Now planes are not completely slipping on each other. What actually is happening? The dislocations are moving. Slip is taking place by movement of dislocation. So the calculated stress required to move a dislocation, it is tau Pn equal to mu exponential minus 2 pi W by B. This is the stress to move a dislocation. It is called as Peierls-Navarro stress. Now to understand this, here you see B is the Berger vector, W is the width of dislocation, and mu is the modulus. You can calculate this, you know this, 2 pi you know this. Now what is width of dislocation? That is very, very important. Now to make you understand the width of dislocation, let's consider two kind of dislocations. One is the relaxed dislocation and another is the unrelaxed dislocation. You can say this is wider dislocation, wide dislocation. This is also, we call it narrow. This is also called as stiff. Now this kind of dislocation are generally present in the metallic solids. You see here the half plane is missing. So once the half plane is missing, these atoms started moving in this direction. Just it is a kind of stress relaxing displacement. But here the bond between these two atoms are so strong, even this half of plane is missing, they are not taking any kind of stress relaxing displacement. You can consider, let us suppose you are traveling in a train and you are sitting in the middle and there are many passengers are sitting, or you can say the capacity is of 4 passengers but they are 8 are sitting. Now at some point you get down at certain station. So what will happen? These 2 passengers will occupy this place, and then these 2 students will also, these 2 passengers will also occupy this place. So this place will be distributed up to a certain number of passengers. If this line will extend up to here, do you think that he will get any space out of it? No, because this space is distributed only up to a certain number of passengers. This is a kind of width of dislocation. So this space is available, this atom slides here, this little here in this side, and they are giving the stress relaxing displacement. So up to how much interatomic spacing the stress relaxing displacement has been taken place is called as width of dislocation. And this Peierls-Navarro stress, that is stress to move a dislocation, is an exponential function of W. So tau Pn, if width of dislocation is 0, like in a covalent solid or ionic solid, then tau Pn equal to mu B, if this width of dislocation is equal to 1 Berger vector, then it is mu by 400 and so on. So you can say covalently strong bonded materials are brittle because they are not allowing dislocation to move. So slip generally takes place due to dislocations, and dislocations are not moving in the strongly bonded material. Therefore, no plastic deformation. And if you remember, if you have a brittle material, the fracture occurs at the elastic limit. So this is how we calculate shear stress required to initiate plastic deformation.